Cool, so my talk is deeply declarative data pipelines, and we'll talk about what that even means. So probably at this venue, most of you probably know these things, so I'll buzz through these quickly, but what are data pipelines? What are we talking about here? We're talking about systems that transfer data between sources and sinks, sort of generally. This includes replicating data with something like Mirror Maker, which I happen to like. It also includes things like filtering, routing, joining streams with something like Apache Flink, ETL and reverse ETL, taking data, say, from Kafka, putting it in HDFS, picking it back up and putting it back in Kafka, that sort of thing, or between offline and online systems back and forth, with something like Kafka Connect or Goblin is under this umbrella. As well as CDC, change data capture, which includes projects like Debezium. LinkedIn's Brooklyn does this. And of course, data pipelines include batch workflows, but for today, we'll focus on streaming for sort of obvious reasons. Okay, so what do I mean by deeply declarative, right? So if you think, there you go. If you think about code sort of generally, it tends to fall along this sort of like spectrum, this continuum of like explicit, concrete, imperative things on one hand, and implicit, abstract, declarative things on the other hand, right? So you might have like assembly language. It's extremely explicit, right? You're telling the machine exactly what to do. It's concrete, it's imperative. You could say that assembly is general purpose, right? Like you can do everything with assembly theoretically, right? And it's internally simple. There's not much to assembly, but it's hard to use, right? That's sort of like one extreme, right? On the other end of the spectrum, you have things like SQL and YAML, which are implicit, abstract, and declarative. That's sort of what we're focusing on today. So the reason why these things tend to be internally complicated but easy to use is because they are domain-specific generally, and therefore they carry around a lot of context, right? Like, you know, there's a lot of like implicit context in what you're expressing in something like SQL or YAML, right? But at the same time, you can't do as much, right? Like, you can't make a website with YAML probably. Maybe you can. You can do everything with YAML these days. All right, so Julian Hyde had a really great analogy that I'm going to steal. Basically, he said, you know, if you're ordering a pizza, you don't call up, you know, Papa John's or whatever and walk the pizza artist through the instructions that ultimately lead to the pizza that you want, right? You just tell them the attributes of that pizza, and you expect them to be able to fulfill that request, right? So that's what we're talking about with declarative, right? You could say, you know, start with preheating the oven to 450, but that's probably a really bad experience. It's actually funny, if you think about it, you don't even have to use the word pizza to order a pizza. If you call up Papa John's and say, I'll take a large, they know what you're talking about, right? That's what I mean by like the context, the implicit context. All right, so when do we need data pipelines? Like I said, maybe you're moving data between sort of like an online operational database, and you want to move it to a real-time analytics database, or you have, generally speaking, you have databases with different sort of, you know, performance characteristics or capabilities, and you want to move or sync data between them. So that's where data pipelines very frequently comes up in practice, right? When we're doing this sort of thing, especially in the present venue, you probably have heard of Kafka Connect. You may have used Kafka Connect to do this sort of thing. So Kafka Connect sort of presents data pipelines in terms of connectors, right? So you have a source connector, for example. You know, maybe we want to get data from MySQL into Kafka. And then you have a sync connector. Maybe we want to get data from Kafka into HDFS. So if you string a source connector and a sync connector together, sort of put Kafka in the middle, you can build a data pipeline that moves data between MySQL and HDFS. So connectors are great. They're already extremely declarative in a sense because you don't really have to write much code, right? You don't have to write any code to get started with using connectors in Kafka Connect. You just have to write some configuration. So here, for example, you know, this is just example configuration for getting data from MySQL into Kafka, right? You have to know like the username and password of your database and how to connect to it, and that's pretty much it. You can also do simple transformations with something called SMTs. Kafka Connect includes this concept of an SMT, a simple message transformation. And with SMTs, you can do things like filter, flatten, that sort of thing on a per message basis. So not only can you move data between systems, but you can also do some sort of basic transformation just using Kafka Connect. Right, so transformations are also just expressible in configuration. So again, they're already very declarative. So now I have this whole pipeline, right, going from MySQL into HDFS with some lightweight transformations in between. And all I had to do was write some JSON for the source side and some JSON for the sync side. So this is a pretty good model. There's some problems you sort of notice right away when I put it on the slide like this, is that there's no pipeline anywhere, right? Like, where's the configuration for the pipeline itself? There is no such thing. There's just connector, and you string them together sort of in your head, right, or on the slide, as it were. This starts to become a little complicated when your pipelines get complicated, right? So like say you have some data in some operational database like MySQL, you're trying to join or filter, do some sort of stream processing across say a change stream and an event stream, and you want to put that into something like Pinot, right? If you follow the sort of connector approach, you can implement sort of part of this pipeline with Connect. But you need something like Kafka Streams to do the real processing, right? Like to do some joins. So within the sort of Apache Kafka ecosystem, you could build this pipeline using Kafka Connect and Kafka Streams. But again, there's no like pipeline anywhere. There's no overarching sort of concept here. There's just pieces that you are fitting together. So we'll talk about Apache Flink as a solution for data pipelines today. Apache Flink, I think, does this really well. One of the reasons it does this really well is that you can sort of like, you can implement the connectors and the stream processing all in one Flink job. So there is sort of more of like one thing, not a bunch of things that are sort of stitched together. I want to take a second and just point out that data pipelines, as they exist today, they're not just replicating between databases anymore. It's not just moving or syncing things. Data pipelines are becoming business critical parts of your business, right? You can do really important stuff with data pipelines, right? So you could have, for example, a Flink job which joins add click events and new account change streams and figures out things like who do we charge and how much do we charge, right? That's pretty important, right? So you can run your whole business as a data pipeline, which I think is interesting because I think we tend to think of like databases as being sort of where the important work stuff gets done, like databases and applications, and then data pipelines are kind of these like dumb pipes where things just flow. But more and more we can do increasingly important stuff in the data pipeline. So I think that's an interesting thing to call out. All right, so hopefully I've sold you that data pipelines are great and easy and have a lot of applications. Or not easy, they're great, they have a lot of applications. How do we make them easy, right? That's the big question. And I'll narrow this question to specifically how do we build data pipelines with as little one-off code as possible, right? So what I'm gonna show you is actually a lot of work up front. We're gonna do a lot of upfront work to build our first couple of pipelines. But once we get all this work in place, once we figure this all out, your n and n+1 and so on pipeline should be super easy, which would be pretty great. That's the goal. Okay, so I mentioned Apache Flink. So I'll give a brief overview of what Apache Flink is and why it's relevant to data pipelines. Okay, so historically, I personally, and I think people in general, have thought about Flink as a stream processing platform, right, or a stream processing framework. So Flink has this thing called the data stream API, and the data stream API is very similar to Kafka streams. You can write stream processing logic in Scala or Java, that sort of thing. And as you can see, this is already pretty declarative in sort of a traditional sense, right? You don't see any like for loops here, right? I'm old enough to remember when stream processing was writing for loops, so this is pretty declarative by that standard, right? As Flink has evolved, they have added the Flink table API. So the table API is when it started to get interesting for data pipelines, because now we have brought this concept of connectors into Flink itself. So you see here, I'm creating a table by configuring a connector. And that table now is sort of like a handle to some physical table or change stream in this case. And I have, I'm using the Debezium Flink connector here for this, which by itself is interesting because if you know about Debezium, it's based on Kafka Connect, but people have taken that Kafka Connect connector and embedded it inside of a Flink connector. So you can now run Debezium inside of a Flink job without like a Connect cluster and Connect configuration and all that. So that's where things start to get interesting. You're sort of like pulling everything into this one thing, the Flink job. And I think connectors are sort of the key there. Once you create a table by configuring a connector to connect to the physical table, then you can do things like filter with where and all that stuff. Right, so the Flink table API by itself, I think, is not that interesting, but it gets interesting. It's sort of the reason behind the Flink table API, in my opinion, is sort of to power the Flink SQL API. This is where things get really interesting. So the Flink SQL API lets you create tables in the Flink table API, and then run queries using SQL. That's it. So as you can see, the process of creating a table in Flink SQL, it's largely just defining the schema for the table and the connector configuration. So here again, I'm using MySQL CDC, which is, I think, based on Debezium. So I have to know how to connect to that database, and how to get the data. But once I've defined that table using DDL, data definition language, then I can operate on that table using SQL and with just select statements, which is pretty nice. I want to point out some point of like potential confusion. I think this is weird. Maybe it's intuitive, but I think it's weird. When you have a create table inventory in Flink DDL, you're not creating a new table. You're really just configuring a connector that connects to some existing physical table, right? So like if I entered a create table and then a select in MySQL, right? I'd definitely get back 0 results because I just created the table, right? I've created a brand new empty table. That's not what's happening here. I'm using Flink SQL sort of reuses these DDL statements not to create physical tables, but to create connectors that connect to physical tables, right? Hopefully that's not too confusing. All right. So Flink SQL is great for data pipelines. Why? Because we can define a data pipeline with just one line of SQL. If I have something like insert into stock select star from inventory where quantity is greater than 0, that's all I need to do theoretically to define a end-to-end data pipeline with some transformation, a source, a sink. So this is sort of like what we want to get to, right? Like if the whole process of creating a data pipeline were this easy, we've done our job, right? Unfortunately, right? So if you sort of winced when I mentioned SQL, right? This might be why, right? If you've used SQL basically the user experience of writing SQL inside of a host language like Java just isn't that fun, right? So this is an example of using Flink SQL within a Java application, and I'm doing string concatenation, that sort of thing. Not too great. Once I write my Java application, which is using the Flink SQL API, the next question becomes, well, how do I get that to run, right? Well, luckily there's sort of a sub-project in Apache Flink for the Flink Kubernetes operator. So with the Flink Kubernetes operator, which we'll talk a lot about today, you just need to give it a location of a jar, and it does all the work of standing up all of the job managers, task managers, and things to get your job running. So it sort of used to be that you needed a Flink cluster first, and then you could submit jars to it to get it to run. With the Flink Kubernetes operator, you just need a Kubernetes cluster, which is pretty great. So if you already have a Kubernetes cluster, you install the Flink Kubernetes operator. Now all you need is a place to store jars, and you can get them running. Okay, so what did a human need to do basically based on what we can do today with off-the-shelf components, right? We had to write some Java, we had to compile a jar, hopefully that's not impossible. You have to store the jar somewhere. This is sort of like an open question, right? Usually, I see these jars sort of like baked into Docker images, but I've also seen them in like Artifactory and that sort of thing. Then someone has to write a Flink deployment YAML. That's the thing I showed on the previous slide, this thing. Once you write the Flink deployment YAML, you can deploy it with something like kubectl. At that point, the Flink Kubernetes operator steps in, interprets that YAML, and then brings about all the machinery to get that Flink job running. So your Flink job's running. So that's pretty great, honestly. It's just starting from baseline, that's not bad, but I think we can do better. So what I'm going to do is sort of walk us through sort of a thought experiment of increasingly declarative, almost to an absurd level, how easy we can make this, right? So the first level is really easy, and I think it's sort of a no-brainer. We can stick our Flink SQL in the YAML, right? Which has some nice benefits. So in order to do this, we have to write a Flink SQL runner application. We have to create a Flink SQL job custom resource definition, and we have to write a whole new Kubernetes operator. All right. So the first part's really easy. You have to write a Flink SQL runner. This is a Java application that instead of like having hard-coded SQL inside, it just loads SQL from some file or from the parameters, arguments somewhere, right? And then executes the SQL line by line. Really easy. And the point behind this, right, is that now I don't have to write Java anymore. So this is the last Java you see for the rest of the talk, right? So usually I get, applause for that, but oh well. Thank you. All right, so you do this once and you're done. And actually, this code was auto-generated by Bing. I happen to know you can do it a lot simpler. ChatGPT tried. All right, so I mentioned a custom resource definition. So if you're not familiar, a custom resource definition is a way to extend the Kubernetes API with additional resource types or kinds, I guess you would say, that you can store in Kubernetes and then can be implemented by some operator. So Kubernetes understands things like pods, deployments, jobs, replica sets. We can, with a little bit of YAML, of course, extend the Kubernetes API to understand Flink SQL jobs, okay? Or at least let us store Flink SQL jobs. So a custom resource definition, a CRD, is basically a schema. The schemas aren't that great to show on slides, so here's the result of doing that work. Once I write a CRD, I can then create a custom resource. And here you see that I basically just have a SQL field, and I threw in parallelism for good measure, right? But basically, I have a YAML file with SQL in it, right? That's it. So this means we now have to write a Flink SQL job operator. So it's not enough to write just a custom resource definition. We need some operator. That's where the logic exists that tells Kubernetes what to do with such a thing, right? So an operator basically takes YAML and then turns it into other YAML. That's one way to think about it. And we either need to turn it into things that Kubernetes understands natively, like a config map or a pod or a deployment or something like that, or we need to turn that YAML into something that some other operator understands. So that's what we're going to do with the Flink SQL job operator. We take Flink SQL job custom resource YAML, and then our operator is going to take that and transform it into a SQL script. We'll use a config map, which Kubernetes understands natively. It's just a bunch of configuration. And a Flink deployment. That Flink deployment is then picked up by the Flink Kubernetes operator, which then turns that into things that Kubernetes understands, like pods, deployments, replica sets, and so on. So this is, how the deeply aspect sort of comes into play. Like we're sort of layering operators on top of operators. All right. So if operators sound scary, I think operators tend to be really complicated. For the use cases we'll talk about today, they're not difficult. All we're doing is we have like control loops that take YAML in and generate YAML out. So they're basically YAML in, YAML out functions. That's pretty much all they are. So the idea behind an operator, right, is a user or an application can submit YAML essentially to Kubernetes, and that gets picked up by some controller, which then generates more YAML, and it's just around in a circle. That's the control loop concept, right? So once we do this work, we can deploy a Flink SQL job using kubectl in the same way that we create a pod, same way we create a deployment, whatever. Kubectl apply, word count, YAML, that's all we need to do, right? And if we get the status of our Flink SQL job word count, we should hopefully see status is running or something like that, right? Okay, so what did a human need to do for this first level of deeply declarative data pipelines? We had to write some SQL in a YAML file. We had to deploy the YAML with kubectl. The Flink SQL job operator steps in. The Flink Kubernetes operator steps in. And then ultimately your Flink job is running. Not bad. Actually, I mean, we could stop here and it'd be pretty great. All right, so there's some problems with this approach. I think the first thing that sort of makes you squint is this create table DDL. This ends up being extremely fragile to write. We don't want like our password in this YAML file, how to talk to a database. We don't want to have like, you know, host names and IP addresses and stuff in this DDL. We don't want we don't want the schema to be like copy pasted across a whole bunch of YAML files. It's just very fragile. So let's think of some ways that we can make this less fragile, so we don't have to write this code a bunch of times. This DDL, the data definition language. So the next idea is to add, of course, table YAML. Let's create a Flink table CRD, custom resource definition, and make our operator a little bit smarter. So the idea behind a Flink table custom resource is you put that DDL in one place, you give it a name, you stick it in the Kubernetes API, and then you just reference that whenever you need it, right? So now our Flink SQL job YAML has references to tables instead of the DDL that actually implements those tables, right? So now we can do, our SQL just becomes like the insert into, and then it references tables. So you can see what the operator would do. The operator would take a Flink SQL job, look up all of the corresponding tables, query the Kubernetes API for the corresponding DDL, and assemble it into a DDL plus SQL script, store that in like a config map or something like that, and then the rest of it is the same as before. Make sense? So there's some interesting things that happen with this sort of approach. We're basically using Kubernetes now as like some sort of poor man's metadata store, which I don't really like. For example, it raises the question, what happens when I delete this Flink table? You could say nothing happens, which I think is kind of weird. Kubernetes isn't just a database. It's supposed to like control things, right? So if I can like create and delete Flink tables and nothing happens, it's kind of weird, right? So I don't like that so much. The Flink SQL job, on the other hand, it's very clear what it means. If I create a Flink SQL job, it means I'd like some Flink, the corresponding Flink SQL job to start running, and I'd actually like actual work to happen, right? Likewise, if I delete a Flink SQL job from the Kubernetes API, it means that I want the corresponding workload to stop, right? Very clearly. This is easily accomplished with Kubernetes. There's this thing called owner references, and it's baked into Kubernetes. It's one of the coolest things about it, in my opinion. The idea is that every object in Kubernetes can have one or more owners, and if you delete the owner, then you get these cascading deletes of everything that's owned by those things. And this happens for free. You don't have to do anything. So that means that if I delete the Flink SQL job, because the Flink deployment and my config map are owned by the Flink SQL job, Kubernetes will automatically garbage collect those things, and this cascades any layers, as multiple layers as you have. So all I had to do is delete this Flink SQL job, and your Flink job stops a few seconds later, right? All right, so let's go deeper, right? Level 3, automatic table registration. The idea here is let's make our data plane and storage layer smarter, and we can do that with a centralized catalog. Okay, so this raises the question, right? Okay, we've gotten to a point where we only have to write this DDL once, but it's still something that we've had to write by hand. Can we do better? Right, and in particular, if you have something like Pinot or MySQL, obviously those systems know what schemas their tables have. They know where their tables are, right? So why is a human writing all this configuration, right? We should theoretically be able to take Pinot table and spit out DDL. So that's sort of what we want to do next. So one way to go about doing this is to use a centralized metadata store or catalog, something like Data Hub. And the idea here is instead of making Pinot, MySQL, and Kafka all spit out DDL, we just, or having our operator talk directly to Kafka, talk directly to MySQL, and that sort of thing. We can have sort of like this intermediate catalog, something like Data Hub, that's a sort of a universal storage for schemas and things like that. So that means that our individual data plane and storage layer databases, the infrastructure that moves things around or stores things, they can register metadata including like schemas and change events with Data Hub. And that means that our control plane, which in our case is the Flink SQL job operator, can just talk to Data Hub to say, what's the schema of this table at the present moment, that sort of thing. So this means that we could theoretically, instead of referencing Flink tables with handwritten DDL, we could just reference data sets in our Flink SQL job, right? So now this is sort of the sum total of everything we'll have to write to get a Flink job running. We have to say, this Flink SQL job needs user item counts and user behavior. Go talk to Data Hub to figure out where it is, what it looks like, and then auto-generate DDL and then stick that into our script. So at this point, you might be thinking that the operator is getting pretty smart, and I think you're probably right. All right, level 4. We can push this model even further by making the infra itself more declarative with even more operators all day. So the idea here is we can have data plane operators, or what I call data plane operators. The idea here is like if you've encountered operators before, you've probably seen operators that control infrastructure, right? They'll like manage Kafka clusters for you. They'll manage Couchbase clusters for you, and so on. You may have also encountered something like a Kafka topic operator and wondered why, right? Like, and especially if you're a Kafka person, you're probably used to talking directly to Kafka. Why would I want to talk to Kubernetes if I could talk to Kafka? Likewise, if you're a Pinot person, why would I just not talk to Pinot? Well, I think the sort of core idea here is if you have Pinot table operators, Kafka topic operators down the line, it means you end up with one unified control plane for creating things wherever they are. Similar to like using Data Hub as sort of the source of truth for what a schema is, I can now use the Kubernetes API as like this unified control plane, which is pretty nice. And so the idea here is like if I create a Kafka topic, the Kafka topic operator would pick it up and then go talk to Kafka to actually create a Kafka topic instead of talking directly to Kafka. Some nice things fall out of this. So if you do this, at least for part of your infrastructure, right, you end up being able to sort of cross-reference between these things in your control plane. So for example, you can have a Kafka topic resource that is owned by a Pinot table. What does that mean? Well, it means that the Kafka topic can't be deleted until the Pinot table is deleted, right? Which sounds pretty great, actually. So like you sort of like, you get garbage collection across your entire ecosystem. Likewise, you can have, for example, a Pinot table that references a Kafka topic just by name, right? Like, go find my topic. What does that mean? It means that we can go look up things like the schema for that topic, what cluster it's on, the bootstrap servers. All that stuff could be stored in the Kubernetes API at a reference. And so now my Pinot table just needs to reference my topic instead of like dumping all this configuration in there. So this has the potential to be really powerful. And of course, if I delete the Kafka topic in Kubernetes, it would, the intended effect should be that the operator goes and deletes the data out of Kafka. If that sounds scary, right, which I think at first blush it does, remember that this owner reference concept means that not only if I delete the parent, will everything downstream get deleted, but the inverse is also true. I can't delete something that's owned by something else unless the parent is also deleted or first deleted. So we'll talk about why this is useful in a couple slides. Actually, the next slide. All right, so level 5 is end-to-end ownership. So let's introduce, finally, a pipeline operator, right? And we'll see how having multiple owners is beneficial. Okay, so The concept of a pipeline, in my view, is basically a bunch of resources that work together to move data from something to something else. So pipeline YAML could just be a set of resources, and those resources could be things like Kafka topics, Pinot tables, Avro schemas, whatever, right? And then ultimately we have our SQL, which is telling us what the pipeline should do. This enables us to have a pipeline operator, which means that there's sort of like this parent object in Kubernetes, the pipeline, and everything that we develop or everything that we deploy as a result of that pipeline is owned ultimately by the pipeline. So these are like the ownership references. So, you know, the pods, deployments, the actual work being done, the workload is owned by the Flink deployment, which is owned by the Flink SQL job, which is owned by the pipeline. Which means, of course, if I delete the pipeline, all this stuff gets blown away. But it also means that if I have, say, a Kafka topic owned by 2 pipelines, it means I cannot accidentally delete the Kafka topic and break, you know, 1 or more pipelines. Because Kubernetes will actually not let you delete a Kafka topic if it's owned by a pipeline, for example, right? So this is really powerful. All right, next level, subscriptions. So this is a little bit hand-wavy, so bear with me. So the idea behind a subscription, in 2 words, I guess, is you manage the sinks. All right, so we've talked about pipelines. I want to introduce like what I call subscriptions, which is sort of like another way of thinking about pipelines. So pipelines, pipelines basically exist to move data, produce data somewhere. So if you think about how you go about creating pipelines, someone needs to first create a sink, for example, a Kafka topic. That user or team now owns that sink. They're responsible for the data in that sink. They're responsible for, you know, compliance, data quality, all that stuff. They own that as a producer, right? Very often that user or team will manage access to the sink. You may have like slacked someone and say, hey, can I use your Kafka topic, right? Like, yeah, let me get you access, whatever. So pipelines, I think, sort of like fundamentally are producer driven. They're built around this concept of like, I want to produce data somewhere. So all the tools sort of speak that language. Subscriptions are essentially the same thing, but sort of from a consumer-driven perspective. Like we want to empower the consumer to get data. We don't care about producing data, we care about consuming data. So some things fall out of that, like why don't we just let the control plane create the sink? Why don't we let the control plane own the sink? Why don't we let the control plane manage access to the sink? Because at the end of the day, whoever is consuming this data, they don't care about owning a topic. They just want the data, right? So, so subscriptions, I think, are very like consumer-focused, consumer-friendly. But yeah, it's a different way of expressing the same thing. But ultimately, these are the same concept. Like you can take a subscription and implement it with a pipeline, or you can take a pipeline and then go find someone who's interested in it and, you know, create a subscription for that. This sort of, you know, to make it a little more concrete, if you think about the SQL aspects of pipelines versus subscriptions, the insert into is actually called a pipeline in Flink, for example. Like if I you know, write insert into Pinot Analytics select star from Kafka my topic, that implements a pipeline. It's a Flink job that consumes from a source and writes to a sink. That's a pipeline. Subscriptions, why do you care what the name of the Pinot table is? Why does it have to exist already, right? So with a subscription, the idea behind subscriptions is you say, well, this is the data I want, select star from Kafka my topic or whatever, and I want it in Pinot, and that's the end of what the consumer cares about, right? So don't make the consumer go create a Pinot table first. Just have the control plane do that for you, is the idea. All right, so maybe you've heard of my side project, Hoptimator, which I'll shamelessly plug here for a couple slides. Okay, so if you haven't heard of Hoptimator, turns out Bing Chat has, which is pretty cool, I have to admit. So this idea of subscriptions, I asked Bing, right, like, hey, can you show me an example of a subscription YAML that can be run using Hoptimator and that materializes a Kafka topic into Pinot? Sure, here it is. And this is the sum total of what you'd have to write to get this pipeline running based on the subscription, which is just a description of the pipeline that you want. And so you see SQL, select name age from Kafka sample topic. The database is Pinot. What that means is that's where you want your data to land, right? I'm going to consume this data from using Pinot or whatever. It goes on to say the YAML file specifies a subscription, materializes from Kafka into Pinot. You can deploy it using kubectl apply file name. That's it. Cool. So take this a little bit farther. So we have this concept of subscriptions, and we sort of equated subscriptions and pipelines. So an interesting thing about the Hoptimator project is that the very name Hoptimator comes from this concept of multi-hop data pipelines. So what do I mean by multi-hop? So if you think about a pipeline that takes data, say, from MySQL and moves it into HDFS, right? That seems on its face very simple, right? There's just one source, one sink. But to create such a thing, you may end up creating multiple hops through multiple systems, right? Depending on how things are laid out at your company or whatever. So for example, you might end up configuring a Debezium MySQL connector. You might end up configuring a Flink Kafka connector, another Flink Kafka connector, a Kafka Connect HDFS ETL connector, and all this stuff, right? And so, probably a lot of people in this room have configured all of these things and got these pipelines running, and they work. But there's a lot of manual stitching and wiring things together, right? And at the end of the day, what we've implemented sort of by hand is just this subscription. Select star from MySQL table 1 where age is greater than 21 or whatever. Okay. So the idea here is we'd like to be able to take a subscription and then sort of turn it into all of these resources, all these configurations, all this YAML that implements a pipeline. And they should all be wired up together, so that this Flink job knows how to talk to this Kafka topic and so on. And ultimately, this is like a configuration generation problem, right? If I have SQL, I want to generate a bunch of configuration, including connector configurations, Flink job configurations, and all that. And that's it. So if you're interested, take a look at the Hoptimator project. It basically does this. I will take your questions.